make it easy for us to, but just, so these are sort of like the supercomputers that are at NERSC, that are at NERSC, and we are using Carver, as the front end. That's what you're compiling, and you could run some of the codes in Carver. As a matter of fact, in Tau, one of the initial problems yesterday is when Samir gave you the instructions and you were using one of the queues in Carver. We have reserved special queues in Magellan, so each of you can get a node, at least one node, and be able to run. But that's why we have to use another system. So just remember, if you need to look at the slides or some of the presentations, if you go to the agenda tutorials, or if you don't remember, just remember axe.nersc.gov, and then there is a link to the Axe workshop, and then you can get access to the tutorials. These instructions that are going to be there, so you have them handy. You can do copy and paste, so you can remember some of the commands we're working. So, we do SSH. This -y, or sometimes people use capital X, and this is so you can get your X Windows environment, between the Carver and your desktop or your laptop, for those of you that are using your laptops. And so remember to source the AxTuts per shell. Every time that you open a shell, you can do it. What we recommend now is that if you're going to be launching, why don't you keep 2 shells open, so you can launch in one, and then you can do all the compilations and editing in the others. Or some of you can open Emacs is also available, or have another editor. For today's tutorials and hands-on, we're going to talk about PETC, SLEFC, and Tau. In any of the modules, you can type module avail, and the name of the tool, and it will give you, all the different versions that are available. At least for PETC, we have the 3.1, version 3.1, and the one that has a small g, and this one is capital O. The O versions are the ones that were compiled with optimization, so they had been optimized. The -Gs, and I don't know what Jed and everybody else is going to be recommending. The Gs are the ones that have the debug flag on, so these are not optimized versions. So these slides are going to be available, so you can, and that's all that I wanted to say. And are there any questions or things that you found in the system? So we want you to have, because the tools are the goal is to highlight the use of the tools rather than spending time, dealing with the system. So as a reminder, today at lunch, if you have questions or you want to go over some of the things that were discussed yesterday, come and see me. So, in here, yeah. So with that, it's my pleasure to introduce Jed Brown from Argonne National Laboratory, and he's going to be talking about PETC.
Okay, so the slides, is that going to go away eventually? That's something separate. So the slides for this talk are online. They'll go on the official PETC website as well, but you can start downloading this now if you want. So I'm going to end up mixing a bit of theory on methods with the usage of those methods in PETC and how to develop code to exploit that. So there's going to end up being some mix, and I would like to get your feedback on how well that works or not. Maybe I should just write this up here.
Oh, they have them in the USBs.
Huh?
They have the tutorials. No? Oh,
These slides? I'm not sure.
No, I don't think.
I don't think so.
So I'm going to put it on the website. I downloaded it, so I'm going to put it there.
Okay. So I'll start with a little bit of introduction and background on PETSI. I'll go through installation really quickly, because chances are you're going to end up needing to install it somewhere, at least on your own machine. And then we'll look at the basic programming model for MPI and for PETSI programs, which are built on top of MPI. How many people here are already using PETSI or other parallel libraries with collective semantics? Okay, cool. And then most of the usage of the library in terms of linear solvers, nonlinear solvers, preconditioning, I'm going to mix into this running example. And you'll be able to download that example as a repository. And this is also an example of how I recommend doing code development. And then there's a second part to this that we'll get to eventually. So speak up right away if there's something you don't understand, if something isn't working, you see some inconsistencies or whatever. If you think there's a better way to present something, let me know. There's a couple of places that you can follow up. So the PETSI maint mailing list is, it's not actually a mailing list, but it comes to all of the developers. And it's private. PETSI users is public. There's also a PETSI developers list. Send to whichever you think is convenient. You don't have to subscribe to anything to send to PETSI maint. That's our help request line. So PETSI was started back in the very early 90s by Barry Smith and Bill Gropp. This was before MPI 1 was standardized, so it was built on Bill's prototype implementation that was used to inform the standard as it developed. PETSI 2 came slightly later. And we've had sort of a long list of developers, some of which stay on the project for a long time, some not so long. So first, in the name at least, we're portable, so we run everywhere from laptops to very big machines, any operating system, any compiler. We do support quad precision now that may be just in PETSI dev, but since the GCC folks have implemented quad precision, that actually works. Usable from a bunch of different languages. The license is very liberal. It's basically a 2-clause BSD license, and our development process is all open, so you can download all the source or all the everything from version control. We run on quite large problems. It even runs on the iPhone. So it's extensible in the sense that every component of PETSI, if you want to make that component be your business, you can extend it arbitrarily. So basically all of the complicated code within PETSI are in plugins, and you can create your own plugins. So as an example, a vendor can supply a matrix format and an associated preconditioner. They can compile that, not distribute the source. Someone else with PETSI code that they don't even have the source available can then load that module in its first class. And that's the case with all the components, not just preconditioners, but coloring algorithms and time integrators, adaptivity, and such things. So we can produce sort of black box algorithms, but for hard problems, black box algorithms usually don't work well. So you don't know what solver is going to work a priori. You have to learn something about your problem and generally experiment a bit to see what kind of structure is in there to develop a good solver. Of course, if your system is something that's kind of a standard example, then there will be advice on what to do, and black box solvers may work. But for hard problems, you're going to end up having to experiment. We want to make that experimentation as easy as possible, preferably where you don't have to write any code to experiment. So lots of methods are available through runtime options. We try really hard to prevent needing to write code to support different classes of methods. So we expose an algebra of composition where you can, because lots of solvers are hierarchical in one way or another, and they reuse a lot of common components. And so you can configure very elaborate solvers on the command line. And we try to keep this decoupled from physics and discretization. Many times when algorithms are first introduced, they're very tied to a certain discretization, and so we try hard to break that. It's used by quite a lot of people, from computational scientists in application areas, people developing new algorithms. A reasonable number of the Krylov methods in PETSI, for example, were developed by people in the iterative linear algebra world as a demonstration of their method, often as the implementation in the first paper on that method, and then they contribute those. So there's lots of exotic Krylov methods that we've acquired that way. And then there's a lot of packages from discretization libraries, more advanced analysis libraries, and domain-specific libraries that are built on top of PETSI. Funding comes from a variety of sources, from applications areas that need some components developed within the scope of PETSI, and some pure computational infrastructure projects. We have quite a lot of examples and manual and such, but please suggest more or contribute if you have an example that you think is sort of representative of something interesting to you. But this is not a silver bullet. Developing PDE solvers for something non-trivial is still hard, and it still takes effort. We provide tools to make that easier. So if you're on many distributions, you can install at least all the dependencies directly. Some have PETSI packaged as well. I really recommend getting the source from Mercurial because it's very easy for you to get patches and to manage what code is there. It's easier to upgrade. So with Mercurial, you clone the PETSI repository and clone build system, and then you can go on to configuration. Our configuration system looks a lot like AutoTools, although it's a Python implementation. But in addition to being able to use packages that are already installed, we can download lots of packages and use them. So you're never required to use the one that PETSI distributes, but a lot of times, a lot of our, say, optional third-party dependencies are very involved to build yourself. And we try hard to make that portable and work wherever you need it. So you can configure with different scalar types and different index lengths and such. So if you solve problems with more than 2 billion degrees of freedom, you may need 64-bit indices, things like this. These options say complex versus real or double precision, single precision, and such are configure time options. So it's not a template library. You have to do that at configure time. So lots of packages we can download automatically, but you can always use your version, which is important if you're using it with a different project. So we keep debugging, or the debug build is what you get by default. You have to explicitly say, I don't want debugging to get an optimized build. And the reason for this is we spend most of our time in code development. We want to get things correct, and so we want the library to do as much integrity checking as possible. So PETSI does lots of things to try to identify user errors and other mismatch when you compile in debugging mode. So please use debugging mode until you really are looking for performance. Then you can switch to the optimized build. It's very easy to keep them both around.
Did you custom roll the Sentinels, or did you use Valgrind for that?
So we have our own, because Valgrind is really slow. It's like 1,000 times slower. So we have our own Sentinels. If you run under Valgrind, we don't put them there so that Valgrind can use its memory management and identify, because it can identify more about what was causing the memory corruption, because it can identify it at the place where you overwrite it. Say the off by one error. Whereas our Sentinels, we only know later when we check it. But
it's lighter weight, you're saying?
Yes, because it's pretty minimal overhead. It can, the debug build, because you have non-optimized flags as well, maybe 3 times slower than an optimized build, but it's not 1,000 times slower. Yeah.
Sorry, what is Valgrind?
So Valgrind, you absolutely must use it. It's fantastic. So what Valgrind, it's Valgrind. So Valgrind is a simulator for your program. So it takes some executable, but it intercepts everything that manipulates the heap, so things like malloc and free, and keeps track of those addresses. And then it watches, as you manipulate, read or write the memory, where that's coming from and if you're really allowed to do that. So if you write to something after you free it, or if you have an off by one error, Valgrind will tell you off by one error here, the memory was allocated here of size this, and this write is out of that memory region. So.
He does other cool stuff too.
Yeah. There's profiling and
Simulation.
yes. So the downside of Valgrind is it's extremely slow. And so you have to run really small problem sizes for it to complete in a reasonable amount of time. But what it does is really slick. And it can detect errors that come even in the MPI stack. So, because you, say, passed in arrays that weren't the right length or something like this. Yeah. None of us have, Okay, so an example. Oops. So this is the repository that we'll end up playing with later. So I do encourage you to download that. It says CSCS because that's the first time I did a tutorial like this with an example with this version of PETSI. So I have that checked out here. Here. So I can compile this thing, and then I can run prebratu-help, and I see a list of options that PETSI gives me for manipulating these debugging features and the options database, which we'll talk about shortly, which is the way we like to configure solvers typically. So we get these kind of options about debugging. The source code there. Is very, very simple. So this is a body of a program that does nothing interesting. Just prints something, and then we'll build a solver for the p-Bratu equation, which is kind of a combination of two nonlinearities. It's not really it's not a useful equation, but it's a combination of Bratu and the p-Laplacian. Okay. And so with this example, I have sort of through the whole history, I have this minimal configuration, and well, let's look at the make file there. So this make file just pulls in the information from PETSI, and we link this example. And in here, in the commit logs, I have lots of example ways to run this. And so, yeah, sort of encourage understanding why, and the slides will accompany that. Okay, so PETSI has kind of a bunch of components that build on the basic MPI stack, and there's profiling kind of throughout because, well, every machine or most machines have some kind of profiling infrastructure, but often it's kind of heavyweight, and it tends to be different between machines. So we have a consistent way to get the information we wanted about performance. And then we have the base, linear algebra and grid management, and then various solvers built on. So the general control flow, we don't take control of main at all. So you call into PETSI at whatever interface level you want to work with, and you provide callbacks that's specific to the kind of problem that you're solving there. So this is all built on top of MPI. This is basically the way that we program distributed memory parallel computers. MPI is a bit over 15 years old now, and really everybody uses it because, well, it's the only sane way. You can run multi-process jobs without a multi-core processor. Yeah? Correct. You can call MPI init yourself, and you can tell PETSI to initialize itself on whatever subcommunicator you want. So the default is that we call MPI init. Well, we check whether you initialized it already, but if you don't do anything, then we will call MPI init. If you call MPI init, then we will just use what you've done. And if you want PETSI to actually run on a subcommunicator, then you can set that, and then we run entirely on the subcommunicator, and we never reference MPI COM world.
So PETSI determining whether or not I've called MPI init is done automatically, or it's something I need to do?
Yeah, because we call MPI initialized, which we're allowed to do as long as the symbols are, because it's there. So remarkably, a lot of people don't get this point. You can run fairly large parallel jobs on your laptop. You can run 32, 64 processes, no problem. And so you can check for correctness. It won't be fast, but you can check for correctness. And often the development environment that you can build on your own computer is much nicer than you can set up on some remote machine. So I encourage doing that. So for shared memory, you can often map memory within a node. So not everything that looks like a copy literally involves a copy. On the other hand, it's much more tricky if you want to actually share some, say, immutable data structures between processes on a node. And so there's still reasons that people like to do threads, but for a lot of problems, you can still program multi-core quite effectively with only MPI. MPI has a lot of features specifically for library interoperability. And this is my biggest complaint about threading libraries, is they don't have these concepts of a communicator and attribute caching. That's really important for libraries to be able to function without kind of assuming too much about the scope that they're running in. The big downside of MPI, or generally of distributed memory programming with any system that can be very performant, is the fault tolerance. So currently, if one process goes down, the whole program crashes with MPI. So you can put lots of options into the MPI exec or whatever your batch submission system is. The popular implementations now have lots of runtime configuration, so you can get a lot of information about performance and tuning and such. when you're using PETSI, you rarely are required to call MPI yourself. So most PETSI examples don't call it. Of course you can. But mostly we have collective semantics. So MPI communicators are really neat. They encapsulate some scope that communication occurs on. You can split them. They make it so that different communication, say between different components in libraries or between different libraries, won't conflict. And within PETSI, there's basically four, kinds of operations. So some are not collective at all. This is just getting local information. Others are logically collective in the sense that every process should call this with the same arguments. But this doesn't actually involve communication, so it has nothing to do with performance. Some are collective in the sense that they communicate with some neighbors, and it's kind of loosely synchronous. This is usually better for performance, but all processes really have to call these. Otherwise, you will typically end up with a deadlock of some sort. Yeah.
So can you tell me how exactly does PETSCOM self work?
So PETSICOM self is just the communicator that's just the current process. So there's many places within PETSI where we've written the code to be correct in parallel. So it calls some MPI operation to do some communication, and that ends up being basically nothing when you're in serial.
So if I want to run a single job within a timer, like if I have like 10 processors,
Yeah.
and I want each one of them to run their own serial job, so serializing within a pipeline environment.
Right. So you can create the PETSI objects that you want to use on COM self, and then they're not parallel objects at all. So each process can do whatever it wants, and they can be doing different things. You can create subcommunicators as well. So you get some group of processes that will, solve a part of the problem. And then the last type here is a synchronous kind of collective. So these are things like norms and object creation. And that involves something like an all reduce. And this is kind of a hard synchronization point. So in terms of semantics, there's not a big difference between these. In terms of, that is, how you call these kind of functions, they're really the same semantic. In terms of performance, these can be much more expensive, but very problem dependent. So this showed up in, it was actually in this RCE cast, which is kind of a neat podcast. There's been a number of cool projects on there. So I see this a lot in this kind of mistake committed by a lot of projects. And so I think this quote from Bill really sums it up quite succinctly. So you want to think about how to decompose your data structures globally. That is, you want to build some consistent parallel semantics. He makes this analogy. Well, suppose you were building a house. You start with a set of blueprints, and you have some idea of what the whole house looks like, and then you would build the parts that you need. You wouldn't, say, start with a bunch of tiles and go glue some tile down and then try to fit it all together at the end. So there's a lot of projects that I think really get this backwards, and they think locally, sort of build local data structures and then try to glue them together somehow and get a parallel semantic. And understanding that code and maintaining that code and debugging problems with it, I think is really hard. So there's some advice. So object creation, we pass in a communicator. We're going to get back a valid matrix object now. It's not all set up. It doesn't have any information at this point about sizes and whatnot. But you can pass that object around, and it will have the parallel semantics, collective on this communicator. So you can set the sizes. We do a lot of configuration from this options database, which we'll look at in a minute. So you can set a prefix so you can identify from the command line or elsewhere to manipulate this object. You can do a set from options, and then you can go use it. So you can assemble and view it and things like that. The mat type here is a pointer to an incomplete type. So the debugger can see what's in there, but your code can't because the definition is in a private header. That's how we do encapsulation. But it's really cheap to, say, pass around and assign and things like that. This option allows you to do things like set the type to, say, a symmetric or blocked format. And there's also there's a few things that you can configure, and the solvers have many more options you can configure. If you are familiar with design patterns, this is an inversion of control. It's similar to service locator, which you'll see in or dependency injection. But this is the way that we configure these objects without having top-level dependencies. Essentially, every object in PETSI, you have a create, you have ways to name it if you want, and set the prefixes so you can refer to them. Naming is mostly for output. You can set the type, because there's usually lots of different implementations, and the types that are valid can be from plugins that get loaded afterwards. There's a setup step usually, and usually that gets called implicitly, say as part of a solve. But in some cases, you want to set things up earlier. You can view any object. So typically, you can view to the screen, and we'll give some summary, or if the object is small, we may print out its whole contents. And you can also view to files or to the screen for visualization. And the help option will tell you what options are available for controlling each of the objects in the simulation. There's lots of ways to set options. So we usually like to use the command line, but you can put these in options files, and you can put them in like a PETSI-RC, and you can insert them from code, and you can put them in environment variables. So if you have some big code and you don't want to give the command line to PETSI at any stage, there's still lots of ways to control these kind of dynamic options at runtime. So as an example, let's go look at this within the PETSI source tree. So this solves the Bratu problem. So we can look at the options here. We're going to have options to control the grid layout. And then we're going to have options to control the nonlinear solver here. And options to control the preconditioner and the Krylov method. So typically this is overwhelming. And so I do, say, filter to KSP or just the GMRes options. In which case, now I've limited down to, to just this much, so I can understand what's happening there quickly. So, oops. So I can pick some problem size. What did I want to do? So here I can see the convergence of the nonlinear method and the number of iterations and why it converged. So these kind of things end up being useful. I'll Yeah. Oh, that one's kind of interesting. Why don't I show that too? Oops. So this shows me the structure of the assembled matrix. I have to change my window manager to see this. There we go. So anyway, and what did I want? Oh, yeah. There we go. So here we're seeing the factored matrix and the assembled matrix on each iteration here. Whereas, say when we do nested dissection, this factored matrix has a very different structure. So you can investigate things like that, kind of convenient. So I will defer this. So this is experiment with a whole bunch of algorithms. You can look at that stuff later. So getting into some of the theory and then usage of the solvers from code. So I'm going to start with a nonlinear problem instead of, say, starting with a linear problem. And we'll get the linear problem out, and then we'll work with it. So our nonlinear solvers are typically based on some Newton-like iteration, which is a defect correction method. So you have some nonlinear system that you want to solve. U is a vector of all your unknowns in the system. We solve for some increment W here. J is the Jacobian or some approximation. So a Picard iteration, which is a pretty common fixed point iteration that people do, is really this same operation, except it's a different Jacobian. It sort of doesn't include all the terms. So Newton methods are quadratically convergent near a root, which means once you get close to the solution, it converges very quickly. So that's a very useful property. So as a sort of example of what the Jacobian looks like, here's a sort of simple nonlinear Poisson problem. So, so if the part inside of this parentheses was equal to 1, this would just be a typical Poisson problem. So we've added some nonlinearity there. And as far as the PDE is concerned, to figure out what the Jacobian was, we can go through and differentiate this with respect to u. And every du that we get, we're going to apply right away to this test function w. So here we can differentiate this piece first, and we get the grad w there. And then we can differentiate this piece, and so we get this 2uw. And the grad u comes along. So this is just chain rule, but for lots of applying this procedure to larger problems tends to help understand the structure of the problem, at least. So if we look here, we have basically this variable coefficient diffusion part, and then this part looks like transport, in some direction w. This is a kind of non-physical example, but that's what we're getting out of this. So a matrix, this Jacobian is a matrix, right? So a matrix is a linear transformation between finite dimensional vector spaces. I don't want to, at the sort of sense of understanding how the methods work, you should not assume that a matrix involves entries. Sometimes those entries end up being really expensive to compute. Yeah, there's an equivalence, but the matrix and the mat object within PETSI is really just a linear transformation. Now, if you form or assemble the matrix, that means defining it in terms of entries. Then you have those available. That's some sparse matrix. So there's lots of matrices out there, right? You know, sparse matrices, of course, we've heard of. Dense matrices, we've heard of. The inverse of anything interesting is dense, but it's also a linear operator, so it's useful sometimes. The Jacobian of some nonlinear function, you can evaluate this with some, say, fixed epsilon. This is an approximation, but this is a sort of relatively easy thing to do that can give you the action of the matrix. Some Fourier transform, other fast transforms, these are also linear. Low rank corrections, Schur complements, these show up in a lot of places in algorithms. But these matrices are dense. We don't want to store those in a sparse matrix or even a dense matrix data structure, because as soon as you store them, you've lost the sort of scalability war. And you'll never have a scalable algorithm if you assemble these things. So, but there's lots of algorithms we can do that don't involve forming these things. They may be sparse, but it's not sparse enough to be all that usable. So as far as computation is concerned, none of these have entries. We can still do lots of things. So one of these is we can use Krylov subspace methods. So the idea here is that by applying the operator repeated times, we can build these subspaces that represent the action of the operator, or rather the action of the inverse, in a useful way. So this, of course, is a really ill-conditioned basis, and so Krylov methods they form variants of this, or orthogonal bases for these spaces. So as an example of what we're looking for, GMRes, I do that in a second. GMRes convergence is dependent on existence of these polynomials that are small on the spectrum. But there's other methods that depend on singular values and on other structure in the spectrum of matrix. But if you have some tightly clustered eigenvalues, then you often have a method that performs well in the sense that it'll converge quickly. So there's this kind of entertaining paper from the early 90s where they take all the popular methods for non-symmetric matrix iteration, and they show these pathological examples where like one method converges in one iteration and all the others take n iterations to converge at all. Usually we don't end up with those kind of examples in practice, but you don't want to have to choose this up front. So GMRes is sort of a brute force method applied to this kind of system. It orthogonalizes this space on each iteration, and then you minimize the residual over that space by basically solving with this Hessenberg form. But it has a clever way to update it at each iteration. So in exact arithmetic, it always converges in n steps. That's not useful because n is like 1,000,000 or whatever. It's the size of your whole spatial discretization. The residual is monotonically decreasing, and so it's often a more robust method than others. I'm not going to go into details of the other methods. In terms of actually, I haven't introduced this equation yet. So the P-Bratu combines two nonlinearities. This piece is called the P-Laplacian. This is actually a really useful problem. It's a very well-studied problem. In the case that P equals 2, and you have some positive lambda, that's called the Bratu problem, and that shows up in solid fuel ignition. So I combine these just because it's two different kinds of nonlinearities. The P-Laplacian part here is singular or degenerate, because if you go put in a grad u equals 0 into the system for any p not equal to 2, you either get an infinite viscosity or you get 0 viscosity, neither of which are good things to have happen. So we'll work with this regularized variant. We can take the Jacobian of this system. That just comes from differentiating through this eta, this effective viscosity. So we get an isotropic part, and then this part is an anisotropic part. So say if p is less than 2, what you're doing is squashing this conductivity tensor in the direction of the gradient. So that makes solving the linear problems a little bit difficult, and this shift as well makes them a little harder. But it's not so bad. So this was the basic structure of the program. So we're going to provide these callbacks to set the function, and then eventually to also set the Jacobian. Solver is going to call back into our code, and we get application state through this context variable. So there were a couple parameters back here. There was the p, the epsilon, and the lambda over here. So we want to put that somewhere so we're not, say, depending on a global variable. So this function we're getting as a callback, it takes the nonlinear solver context, the state vector, the residual, and then our context. And what we're going to do is evaluate some residual, and we're going to, based on the state x, and we put it into that vector. If we provide a Jacobian, then we have the same kind of initial part here. We have the nonlinear solver context, which we can query. You don't. Sometimes there's information in there that you wanted to know about. And then there's the state that we're evaluating around. And then we provide the Jacobian. And you can also provide preconditioning information. Very often these are the same, but sometimes we'll make them different. We'll make them different in this example. So instead of providing this Jacobian, you can use coloring, which does this sparse finite difference assembly. You can use matrix free and hopefully provide something else for preconditioning, which I'm deferring slightly, but we're going to look at preconditioning in a few minutes. You can do automatic differentiation for those Jacobians as well. And for this problem, we're going to solve it on a structured grid. And so rather than do all the grid management in the example, we'll use this, the DA object within PETSI, which manages the distribution on structured grids. And it also lets us do multi-grid. It'll give us a refinement hierarchy. So the basic idea here, we need to compute residuals on the region that we own. And in order to do that, we have this differencing with neighbors. And so you end up needing some fringe region here. You need to communicate these ghosts. So and it's the same kind of thing occurs in unstructured methods. So we're going to communicate to what we call a local vector. The local vector is going to contain everything, including these ghost nodes. And then we'll go compute the solution inside. So when you think of a structured grid, often people want to number it like this on the left. And this is really convenient for, say, determining where to implement boundary conditions. On the other hand, internally, there's a decomposition that's in the order of the processors. And this is because this gives you the communication structure that you wanted. You would have to do some indirect addressing otherwise. So, yeah?
Explain natural numbering.
Yeah, well, so the natural numbering is just going through your whole grid, and it's, say, the lexicographic ordering for the whole grid. It's decomposed in parallel, but this is kind of the index that's natural for the problem. For unstructured grids, usually there isn't a natural ordering that's all that natural. And so you end up using an ordering like this for your computation or for logically thinking about the problem as well. But for the structured grid case, writing loops over parts of the domain and checking whether you're near a boundary condition or things like this is easier to do over on this side. So our structured grid abstraction lets you have this decomposition and get the ghost values and whatnot, but you can write loops and index as though you were in this region. And this is a lot like the global arrays philosophy anyway, although the implementation is a bit different. Yeah?
So then is there communication when you're looping over? So you're saying that...
No, because you get out a local vector that kind of includes this section,
Okay.
and then we fix up the pointers so that when you index, in these coordinates basically, so when you index at say 3, 2, which would be this slot, the say x coordinate of 3 and the y coordinate of 2,
Processor
right?
0 is going to say, I don't own this processor 1.
No, you communicated it already, and this is in your local memory, and the pointers just point at it. I'll show you. I'll show you.
That's what you're saying.
Yeah.
Okay. Yeah, gotcha.
Yeah. If you try to index outside, but within those loops, then it's an out of bounds memory access.
Okay.
But you can define how much ghosting you want, and then the ghosting that you wanted will be set up so the indices point in there. It's just an interface convenience. So, this is what's going to sit inside of a local vector, and we're going to fix up indexing so that you can index this like it was sort of the complete thing, and you're not allowed to access out there. So the DA really only contains this topological information and perhaps coordinates. It doesn't really have a discretization in it. And so it's just to manage the communication for you. You by no means have to use the DA, but if you have a structured grid problem, it's very convenient for simple examples. There's global vectors and local vectors. So the global vector is the thing with the parallel semantics. The local vector is split out. So for example, I can have this big parallel vector, and it's decomposed. There's, say, rank 1, 2, 0. So if I do a dot product on this, or I add this to another vector or something, it happens across all of the processors. Everybody is supposed to call those functions. And then there's these local vectors, which are totally independent. And so this part kind of maps straight over into this, this local part just gets mapped over. And then there's some ghost values that come in to fill in the rest of that thing. Huh?
More than one, right? More than one ghost value is stored.
Yeah, typically. So depending on your discretization, you may need first neighbors or second neighbors, and you might need corners. And so working on the DA, you have this global to local begin and end. And so that's what does this scatter. So it moves from this parallel vector into a local vector. And you can contribute values the other way as well. So you can insert or add, or take maximums and things like that. That gets you this piece that you're going to work with locally and involves no communication while you're over here. We split it into begin and end so you can overlap that with some computation if you had some to do. And then there's a local to global that can go back the other direction. So depending on the discretization, you may want the neighbors just along the Cartesian directions, or you may want corner neighbors. So when you create the DA, you get to specify that. The interface for this is much nicer in PETSI Dev, but since we have 3.1 here, 3.2 is going to be released next week or so.
What if the discretization does not use ghost points?
If it does use ghost points,
It does not.
oh, it doesn't use them at all, then you can set that to the stencil width can be 0, and then it doesn't communicate anything. But you can't do a differential operator that way. So if you have reaction or something on a structured grid and then some other part of the computation is going to use it, or for whatever reason it's like really purely local, then you don't need any ghost points. But if it's a differential operator, you need to communicate something. Otherwise, the subdomains would be totally independent.
Yeah, you're right.
So.
Well, being ghost points in the sense that the domain is the local array.
Sure,
Yeah.
but if your problem is actually like independent on the, say, I don't know, you have two different materials or something, and somehow they don't talk to each other at all, or they talk to each other through some other mechanism, then you can make the DA for that just live on a subcommunicator that's only managing that structure.
What you're calling those points here is not like points that you create out of your domain to compensate. It's just
No, so this is to talk to neighboring processes. Yeah.
Okay, cool.
So here we have better support now for if you want ghost points for boundary conditions. So periodic puts information there, but also does communication, and so there's a few variants of this, and the support for those variants is better in PETSCDEV. So there was this box or star stencil, the number of points locally or number of processes, the number of degrees of freedom per node. And you can get finer grained control over exactly what the distribution is, but most examples don't use these last arguments. So the 2D and 3D version and 1D of this. Yeah?
But problems can live on different parts of a zone, mainly at the zone center, at zone faces, at edges, and so on and so forth. What do you do with that?
So people do different things. Sometimes they map it as though there were several degrees of freedom at a corner, and then they write a special interpolant for multigrid. Other times they use different DAs for the for say pressure versus velocities. It depends a bit on the problem and how you wanted to write how you wanted to break things up in terms of the code modularity, which one I would recommend.
I've seen it multiple using that to different DAs.
Yeah. So it's a matter of how you wanted to store the memory, right? So if you want the memory to all be interlaced into the same thing, then you use one DA. If you want them to be separate, which is also real convenient if the preconditioner you're going to end up using wants to take them apart.
But if you also think from the abstract point of view, it's even easier to think that you have different DAs depending
Yes.
on where your actual values are.
Yeah. So I will talk about multiphysics later and kind of recommendations for problems like that. But there is this object called DM composite that you can glue together separate DAs or even like DAs and global parameters. And the preconditioners use that to kind of inform ways that they can take things apart. So you don't need to use it, but it's convenient sometimes. So when running on a DA, you can provide these local callbacks, and you just have to do a little bit less bookkeeping. And so we'll end up using that in this example. When the nonlinear solver goes to evaluate a residual, you're going to typically do these scatters, or they can be managed through the DA to get out the local vectors. You evaluate the residuals on the local vectors. And then, in this case, this piece actually takes care of putting those back, perhaps into a global vector. So this local function, we just have fields that come in, and we have this information about the array. Yeah, this is just a simple structure that has the decomposition in it. And so you roll loops over your local part. And this is kind of the simplest interface to use. So an example here for the Bratu problem, you just have a loop over the 2 dimensions of the structured grid. The value u, which we're going to use up here, is just the value at that point. This is the finite difference stencil. And here we just set the residual at that point equal to the sum of those. And so we've multiplied through by this volume element, which is something you usually want to do to have the problem be well scaled. So this is where all the physics is sitting. There's a few conditionals, say, to handle boundary conditions, but this is the physics for that problem. So we can go back to that example. Oops. We can update to revision 3, build it, and so this has a few examples in the commit message. So we can run these, and we can look at, say, what happens when we refine the grid. And so the number of nonlinear iterations stays constant, but the number of linear iterations is going up here. And if we go to a much bigger problem size, it goes up more. So what we're doing here for the Jacobian is this matrix-free finite differencing. But remember, all we've written for this function is this. So we can check that this is correct. And if we know something about the solution, we have a small benchmark problem we can run. We check that this is producing the correct results. And then we will never modify this again. And as long as the nonlinear residuals, that is what we were looking at here, as long as these nonlinear residuals get small, we know that we're solving the problem. So this is in contrast to a lot of, say, semi-implicit, or there's a lot of iterative methods where you don't have this residual in hand. They claim to be solving some equations, but there's lots of complexity in the algorithm for solving those equations, and you don't have some kind of hand on whether you're getting the right answer. And so here we, because we're going to verify it as the very first step that we're getting the correct answer here, and then we'll never modify this bit of code again. So the actual code for this example, it does some setup, and it pulls in these parameters. We have an initial guess, which was pretty simple, and then this is the code here. This is actually only, so this is the Bratu problem from the slide before. So it's not P. Laplacian yet, but we only implemented the Bratu part. Okay. So now we can add this P nonlinearity. We're going to keep doing this, really the same thing that we had before. So we can look at the patch here. So I have a commit message. This lets you kind of have some examples to run. And here we were just evaluating some quantities at various staggered points, and we go evaluate that effective viscosity at these staggered points, and then we put it into the end form. So now the rest of that physics is in there, and we can check that we get things correct. So we compile it. We can run here. Okay. So basically as expected. The iteration count's going up. So we don't want that linear iteration count to keep going up. So we've been mentioning this a bunch, but haven't gone into details yet. So we're going to use some preconditioning. There's left preconditioning and right preconditioning. They're not. They basically do the same thing. The difference is what norm you end up working in. You never form this product. You never assemble P inverse. But P inverse is some operation that you can apply. And the goal is just that this product, P inverse A or AP inverse, is well behaved in terms of, say, having a well-clustered spectrum. So a preconditioner, or a preconditioning algorithm, is some method for constructing this linear function, which is P inverse here. Okay, so that's what's showing up in these kind of problem definitions. So we're going to form that using this operator A and some extra information I call A sub P. Okay, and that A sub P is the preconditioning matrix. And all throughout PETSI, you have plumbing for both of these. You have the operator and the preconditioning matrix. Very often, they're the same thing. But in lots of important cases, they're not the same matrix. For example, A might not be assembled at all. A could be one of these, say, a tensor product. And AP could be some sparser approximation to that. So the P inverse is dense. You actually don't ever need P. It's just a notational, thing. This operator A is rarely used, but sometimes you use some nested method as the preconditioner. So it's in there. The A sub P is very often some sparse matrix. There's matrix-based methods. These are sort of purely algebraic, and they use assembled matrices, and they do some decomposition. And then there's various classes of parallel methods and for indefinite problems, or like stiff wave problems where you have to do extra things because these methods tend not to work well. So when you see a matrix, yeah.
Is there anything that you can do for the matrix field?
Without knowing anything else about it, there's very little that you can do. So you can do, say, you can do some other Krylov method, and you can nest that. So occasionally, if, say, GMRes is the only thing that works, but GMRes restarts cost you a ton, you can do these GCR or a flexible GMRes, which is a method that's tolerant of these nonlinear preconditioners. And you can do a nested iteration, and sometimes that's better. That is, you use some cycles of a Krylov method as a preconditioner for some other Krylov method.
Are you asking a slightly different question? Are you asking whether...
So this is about the nonlinear part, right?
Well, this is now solving the linear problem that we need at each step of the nonlinear problem, or from wherever else. This is general, actually. It applies to any linear problem. But if all you have is the action of the matrix, you have no other information, then basically all you can do are iterative methods that apply the action of the matrix. If you have, say, an estimate of the eigenvalues, then you can do smoothers that target some region of the spectrum.
How do you improve these things? Yeah, if you do have an eigenvalue estimate.
Well, you can get an eigenvalue estimate even from a few cycles of a Krylov method. So if you can target part of the spectrum and you have, say, some other way to pick up the rest of the spectrum. So, for example, if you have some sort of multigrid, but it's maybe an integral operator. So this is a, I'll try not to spend too much time on this. So in an integral operator, you basically just have its action because it would be way too expensive to assemble. But there you have these high energy modes and they're long wavelength. And then you have lots of short wavelength modes, but they're all pretty low energy and they're pretty well clustered near one. So if you have some hierarchical structure where you can represent the long wavelength modes in that hierarchy, then you have a way to filter the high energy modes. And then you can go use it like a Chebyshev smoother, something that targets the low energy modes, which were the short wavelength modes, the local part. And then the other levels of multigrid will take care of the rest. So there, what you actually use is basically only the action of the operator, except you also had this hierarchy available somewhere, that allowed you to, because you're kind of separating the scales and targeting what you needed. So that's called multigrid of the second kind. If you're, but these are the kind of things you can do. But as a black box solver, if all you have is the action, you have very few options. So you want to look at the spectrum and say, like, what kind of structure do I have? If you know something about this, this will tell you kind of what class of methods might work well. How dense is it? Is it a thing that we might want to assemble? Is it, where methods that use assembled matrices might work well? There's some fast way to compute its action. And some way to approximate its action. So that's basically, how are we going to precondition it? And for most problems, that's what you want. So relaxation, we can write as a preconditioner for some Krylov method. These kind of classical relaxation methods. We can just take this piece, the interesting bit, so the diagonal, or say the lower triangular part, and those correspond to these classical methods. There's factorization, which internally involves a symbolic factorization where you figure out where there's going to be fill, and then a numeric factorization that computes the entries there. So LU decomposition is the ultimate preconditioner. It solves it in one iteration. The trouble is it's so expensive that you often don't want to use it, but having it available is good. So for PDE problems in 2D, you need m log m storage, that is for matrices of dimension m. You end up needing m log m storage and this m to the 3/2 time, or floating point operations. And in 3D, this is a bit worse. It turns out storage is often the limitation, especially in 3D. So none of these scale, because you want O of m for both time and space. And symbolic factorization is often a bottleneck in parallel and usually not a big deal if you're doing local problems. Incomplete LU skips fill in one way or another. It tends not to be a good method in parallel, but it's a very practical method locally. So the theory is horrible in the sense that you have very few guarantees about what ILU will do, but it's a still very practical method. Domain decomposition, which is what a lot of the kind of basic solvers within PETSI are based on one-level domain decomposition. So you can do it with overlap and without overlap. So this is some decomposition where the subdomain size is big H and the element size is little h. So this ratio big H over little h would be like the number of elements in a subdomain. And L over big H would be the number of subdomains to get across the domain. With a one-level method, if you do no overlap, then you get these kind of estimates on the asymptotics for an elliptic problem. With overlap, you get these sort of estimates. There's problems based on Neumann problems. So these are, you need these unassembled matrices, or where just the local part of the matrix is assembled to have these Neumann problems. And they have a little different estimates, typically. There's exotic versions of Schwartz that have estimates that look more like this. The important thing is you can take off this leading factor of L over H if you do a multi-level method. And so this, the number of iterations then becomes this logarithmic term, or up here becomes relative to an easier to satisfy ratio. So multigrid methods are kind of the prototypical scalable algorithm. So the idea here is you have some coarse space and a fine space and a way to get between them. And then you're going to have some kind of operation that takes care of the high-frequency modes. That is, everything that wasn't going to be represented on the coarse level. So you can do this decomposition geometrically in terms of, say, levels of refinement of a mesh. And you can also do it algebraically, which just uses the matrix data structure. You need, often anyway, assembled versions of some coarse operator. So you can do it by a Galerkin procedure, which means, say, interpolate to the fine level, apply the fine level operator, and then bring it back down to the coarse level. And if you go assemble that product, you get out a coarse level operator. That can be a sort of expensive thing to compute that product. So there's reasons to like geometric. And then you can use any preconditioner as the pre-smoother on some level. You'd say go to the coarse level. You solve maybe approximately there, maybe recursively by multigrid, and then you bring it back to the fine level and post-smoother. And there's variants of these kind of methods. So textbook multigrid convergence is where you get up to the discretization error in the method in a constant number of iterations, and typically a very small number, like on one hand. So most of the theory applies to symmetric positive definite systems, and even most of it is even targeted towards just the scalar case. But there's fairly developed theory in terms of what to do when you have variable coefficients, when you have anisotropy, to some extent dealing with complicated geometry. But those are the kind of things that they're still within the analysis framework, but they make the methods more technical and might make black box approaches not work well. And then there's deeper algorithmic difficulties if you have a non-symmetric problem. So like a transport-dominated problem, compressible gas dynamics, for example, or an indefinite problem like incompressible flow or Helmholtz or Bad Maxwell. So in terms of parallel performance, you want to have some kind of aggressive coarsening. Most of the theory uses some like Gauss-Seidel or over-relaxation smoother, but ILU is more robust for some problems. And the coarse level is often distributing the coarse level and solving that as a kind of important bottleneck. So often it's done somewhat redundantly, or it's just done approximately and you pay in terms of it not being quite optimal. And the multi-level Schwartz methods are really the same algorithm, just explained in different language and with attention to different details. Finite difference Jacobians. So this is if you didn't want to write the code to assemble the Jacobian yourself. You can compute a dense version, like really with no information at all. You can, if you know the sparsity pattern for the matrix you're trying to compute, then you can do it using colorings. And so there's some examples that will do that. And then a really common thing is that you, say, assemble an approximation, and then you want to use that as a preconditioner, and you'll apply the true operator matrix free. So this is something that's used in practice a lot. And that's where those two slots, one for the operator and one for the preconditioning matrix, come in handy, being different. So let's try this out on the example. So we can update it. So here, we set up some options to do this in code. So this is to do the coloring. These are just two different parallel semantics for how the coloring is done. This is even providing the own your own code for doing the coloring, although you don't have to use that. So, oops. Let's take an example here. Okay. So let's see. This problem, because of the parameter range that we're in, converges. Newton takes a long time to converge. It converges really fast right at the end, but it has to get pretty close to the solution. It takes a long time to get there. And then we're viewing the method that's actually used. So there was this -SNES view down here at the bottom. So that's viewing what's actually happening. So we have the SNES is this nonlinear solver object. We're doing a line search. These are parameters for the line search, number of iterations and convergent tolerance and such. The linear solves are done using GMRes here. We can see parameters for GMRes, left preconditioning here, what norm is being used. The preconditioner is an incomplete LU, so we can see, say, what's showing up in the factored matrix there. And then, why it converged down at the bottom. And if you have a kind of a more sophisticated solver, then this will give you all the details of the various levels of nesting. So it's pretty useful to be able to read these. Let's take one of these examples. Okay, so here we ran in parallel, and we used we used this FD Jacobian. Whoops. So that was this is using the library provided way to compute the Jacobian with coloring. So we can see the number of iterations and such things here. And this was running in parallel. So we're using block Jacobi to manage the parallel decomposition here. And then the preconditioner inside of each of the blocks. So this is kind of the subdomain solver here, is an incomplete LU. We see the parameters for that and the size of that. Because we ran on 4 processes, the size of that is 100 by 100. And so each process has one of these things. So we can run this with, say, algebraic multigrid, and there we see the number. We see the number of iterations be kind of smaller, and we can scale up the problem size, and it should stay fairly small. And then here we see this whole multigrid hierarchy, where we have the course level problem, in this case being solved redundantly, sort of this bit, and then we have on levels the information about what's being done there. Yes. So we can also use Boomer AMG from Hyper, and so we see what that's doing, kind of smaller iteration count, And that's typical, actually. Boomer AMG usually has fewer iterations, but higher setup and memory costs. So, and we see, whatever parameters were used for that. So we can experiment very quickly. And we can change the algorithm to do the finite differencing. And on this problem, when you play with it, and if you stress it, you'll end up having to change this. You go into more extreme parameter ranges. So back to matrices, or rather we want to assemble matrices, right? So my snarky response here isn't very useful because we want to, say, avoid doing this coloring because the coloring is kind of expensive, especially for 3D problems or for vector problems where we have a lot of unknowns. So let's kind of get back to the matrix and assembly interfaces. So we have a number of different formats. Generally, you don't have to touch your code at all to change the formats. And we can use them with a bunch of external packages. So the usual kind of interface, we have creation, setting sizes, types, options so that we can control those pieces from the command line. There's pre-allocation, which ends up being important for performance, and this is maybe the messiest part of the whole business. But for a lot of problems, you can pre-allocate, or figure out how to pre-allocate easily. If your problem has some blocks, then you can use these interfaces. So you can set the block size, and then you can use a set values for the blocks. So if you have, say, a structural dynamics for structural mechanics problem, you have, say, a block size of 3 for the displacement variables. All of the indexing and metadata in the system can address that whole block size instead of just the individual scalars. So you have the usual interface regardless of the format. You can choose the format at runtime. So for scalar problems, you'll usually just use the common AIJ data structure. For block and symmetric problems, you'll use those. But most external packages don't support these block formats. So when you want to try the external package, you may have to use the scalar format, which is less efficient, but they can use it directly. So the matrix assembly, you have some loop over your domain, and you're going to end up calling these mat set values. And I think the slot point is out of order. Oh, no. It's in order. It's just nested differently. So each process is going to call mat set values, typically on parts of the problem that it is responsible for, like that it owns those rows of the matrix. But you can set any off-process rows as well. So, and then we do this mat assembly begin and end. There's communication that happens inside of there. And of course, you can overlap that if you have other computation to do. In the case of blocks, the row and column indexes refers to the blocks, and then you have all the values. You can call the blocked version even if the matrix format is scalar. So one way to do this would be to have rank 0 just loop over the whole global system, and these are boundary conditions, and set the values in there. This is horrible because it involves way more communication, and only rank 0 would be doing any work. So a better way to do this is to have every process loop over basically its local portion. So the rows that it's owning, and then the body of this is exactly the same code. I've actually been through most of these points. So sometimes you do want to set off-process values, and even not within some really restricted predefined structure. And so we haven't found this to be any performance issue, and so we allow you to set values anywhere, and we figure out where they go. But if you want something high performance, you should try to set values locally as much as you can. So finite element methods, you tend to set values that are on the interface between subdomains from both processes.
But sometimes like when you're computing the stiffness metrics, you may have to do set values in a different rows and columns that are not necessarily.
Yes, so you can call the mat set values with any row, right, including rows that you don't own at all. And we manage that behind the scenes. And the mat assembly begin end is where all the communication happens. So this one is local, but this one would be setting everything from rank 0, which you could do. But you can call mat set values with any row and any column in the matrix, and it will find its way to the correct place in the mat assembly begin end.
So I noticed you have mat assembly begin and then immediately after mat assembly end.
Yes.
So that suggests that there are other things that you can do after beginning but before ending.
Absolutely. If you have anything interesting to do, something else in your simulation to compute, you stick it in between those.
So, okay, so the things that happen above, that's not part of assembly.
Yeah, this mat set values is not calling any communication functions. It caches values that need to go to other processes, get stashed locally, and they get communicated in the assembly begin end.
So what is an example of an interesting thing that could happen between those two begin?
So if you had a finite element problem, you'll be using add values here. And you'll be setting values from every process that's integrating on an element that touches that node. And so you get values coming from several processes at say a node that lies on the corner of subdomains. But there's also cases where there's the worst is when you have some kind of like really fast connection, or you want to pin together structures. So if you have self-contact, for example, then at some point within the simulation you'll have points that used to be really far apart that then are suddenly together. And the assembly process for that, you may have this kind of unpredictable entries going into off-process values.
Is this
Yeah.
like a barrier process then? So if I'm assembling multiple matrices?
You can call assembly begin on all of the matrices, and then do work and call assembly end on the rest of them.
It's still a barrier, nothing will proceed until the last assembly end is completed?
So every matrix you're assembling is independent, and you can't use the matrix until the assembly end is called. And the assembly end is blocking. The begin is not blocking because it just puts out some requests, basically, and calls asynchronous sends on some of the buffers. So every process needs to call these. Assembly begin technically does block because there's two steps of that communication. So you couldn't, if you had like if rank 0, begin A, begin B, else begin B, begin A, you would have a deadlock. But if you don't do that, then it's no problem, and they're all independent. And you can complete one and the other ones can be in flight, and you can use the one. Okay, so assembly for pbratu. We'll just look at that code real quickly. Go here. So this sets a few basically grid size points, and then this is just assembling the Laplacian part. So we set some indices here, and we have the stencil. So these are the off diagonal bits, and this is the diagonal part. And we're using the set values stencil, so we can use the indexing that was showing up over here. And why don't I do this? I'll do this one example. Oops. I'm not going to well, how about here? Oh. Okay, maybe I have a problem there with, I'm not going to hunt that down right now. I'll have an explanation for that later. So the question, and we'll do this interactively in the afternoon, but the question is, what were we going to do with that, say, big anisotropic part? Because we had the fairly complicated code for the residuals, and the Jacobian assembly for that is kind of messy to code. And so there's some experimentation we can do there to determine whether it's going to be worth writing the code to assemble the exact Jacobian or not. And I think it's kind of a slick demo. Debugging tips. So we use this checkmemq internally a bit, and that sort of checks for these memory access problems. If there's anything that isn't obvious there, it's very useful to try Valgrind. Work through that. Let's see, how much time are we looking at? Okay. So how many people here are kind of working with an existing code base versus more or less starting new projects? Okay. So we want to find some way to compromise between, say, modifying existing code to go to great lengths to be friendly for the solver versus, say, not modifying it at all and making the solver algorithms work around something that's sometimes not a good interface for the solver. But so the profiling here and the experimentation that we can do to figure out whether it's worth investing the effort in writing these components, I think is an important aspect. So I discussed this earlier about being unintrusive in the sense of not taking control of main, not referencing MPI-COM world. You can wrap existing data structures inside of the various shell objects, and those can be first-class implementations. So you have existing data structures. You want to use it with some components of our algorithms. You can wrap it as a matrix or a preconditioner or whatever piece you want. You can also use your memory internally, although in the case of matrices, to use your memory exactly with our matrices, they would have to be using the same format already. a common one that comes up is you want to do some more implicit method, but you had a preconditioner for some semi-implicit method hanging around, so you can reuse that. That's a common case. You don't have to use the high-level interfaces, but if you use them, then there's extra things we can do. Of course, always do version control, profile as much as possible, and experiment before investing a lot of effort in writing. So sometimes there's an inefficient algorithm we can use, but part of that we can profile and say, if we made this inefficient thing efficient, we'll see how the algorithmic performance is and know whether it's worth writing the efficient version. So we discussed this earlier in terms of you can set the communicator that PETSI will use. So you can initialize PETSI on a subcommunicator. We normally compute the logging stuff inside of PETSI finalize. PETSI can only be initialized once. Actually, it can be initialized more than once now, but I don't recommend doing that typically. It's more confusing. So it's important to pre-allocate matrices, and this is kind of the dirty part. I have so for the AIJ matrices, you basically just need to know the number of non-zeros in each row. And if the number is fairly constant, you can just use some, say, upper bound. So if you have a 7-point stencil, you can just put 7 there, not worry about this. And the boundary conditions where it's less than 7 cause no problem. For parallel matrices, yeah?
What if you don't know a priori how many non-zeros you're going to have? Is it just slower, or is it?
It's just slower, but sometimes it's a lot slower.
Okay, but that's a one-time thing because...
Yeah, you only pay it the first time.
Yeah, so if throughout your problem matrix structure doesn't change,
yeah,
and it's one-time allocation.
Yeah.
Problem. Okay.
It's highly recommended. Otherwise, really...
It's much better to set some upper bound on what you expect.
Right, like if you have some unstructured grid, there is...
So there's absolutely ways that you can determine that even on an unstructured grid. There's fast traversals that you can do that will get you that information. But unfortunately, it is more code to write. It's not just you call your assembly. So the parallel matrices that the formats that we use primarily decompose into these diagonal and off-diagonal blocks. And the reason for this is overlapping the communication computation inside of the matrix multiplies and such, as well as being able to form a lot of common preconditioners that use the diagonal block independently. So for pre-allocation, we end up needing the number of non-zeros in a row in the diagonal block and in the off-diagonal block. So you can give kind of upper bound estimates, or you can give a by row value in there. You can run with an info, and you'll get information about the number of mallocs, so you can check that you're getting the correct pre-allocation, or kind of how much space you might be wasting. Well, so this one is over-allocated for this small size, so there's a number that are unneeded there. So the block formats have a static block size. The symmetric ones just use the upper triangular part. As far as the assembly code, that's totally unchanged. But if you change from, say, non-symmetric to symmetric format, the pre-allocation is different. You can just call all the pre-allocation functions, but what you needed was a little bit different. For Krylov methods, you just need to be able to apply the operator, and you call this set operators if they change, and then the method will use the updated values. If you want to solve several systems with the same, like several right-hand sides with the same system, you just call KSP solve multiple times. and you can pull out the sub-objects and configure those as much as you want. But we like using the command line or configuration files. We looked at this already. So the bottlenecks that we typically run into are related to matrix assembly. You have some floating point limited local computations typically. So these are, say, equations of state and integration and basis function evaluation, things like that. And then inserting values into the matrices, and that's there's a search within a row that typically happens, and so there's some branching and some irregular memory access. Preconditioner setup, constructing and say factoring course level operators is a common bottleneck, and extracting overlapping subdomains is another one. Preconditioner application typically looks like matrix multiplies, triangular solves. Relaxation looks like a triangular solve as well. These are basically memory bandwidth limited. So modern CPUs support a really small fraction of the memory can only support a really small fraction of the floating point unit. So, unfortunately, if you're going to use sparse matrices, you're going to end up being limited by memory bandwidth. If you can use matrices in general and do sort of single right-hand sides, then you're limited by memory. If you apply operators matrix-free, then often it moves over to the floating point unit. And, of course, there's algorithmic things like globalization may take a lot of time, but that just means you have to kind of do more of these operations. So the basic summary on scalability, there's strong scalability, which is where you end up with very small subdomains because you had a fixed global problem size. And what you want is to be able to solve that problem fast. And there's weak scalability where you have typically reasonably big subdomain sizes, and you want to solve big problems. So you want the time to stay constant. And these are strong scalability is not actually a stronger statement than weak scalability. Sometimes weak scalability is harder to attain in practice. But these are the two cases we're concerned about. The easiest way to make software scalable is to make it sequentially inefficient. So scalability is really easy. We want efficient software. So for that, we want to have a performance model. So this is in terms of memory bandwidth and latency, sometimes in terms of floating point unit, often in terms of some network operations that become really critical. If you want to demonstrate that your program is efficient, you really need that performance model and to show that you're at some reasonable fraction of that performance model. Showing that it's scalable is not it only shows you the marginal benefit of adding more cores. It doesn't tell you anything about doing science in a reasonable amount of time. Often there's huge constants hidden in the choice of the algorithm or in the implementation somewhere. And so you want to be able to kind of draw out those constants. Drawing out these is quite difficult frequently. But this is now a few years old, or maybe 3 years old, but this is similar to what we have now as well. So we have some kind of hierarchical memory. So there's local caches on the core, some shared caches. You talk through multiple layers up to memory, and now these buses are split apart more, and so you have more levels of separate memory banks. So these have vector instructions on the cores, which sometimes we want to use. The number of flops is almost irrelevant for sparse linear algebra. It's all the bandwidth that matters. So these sparse kernels are sitting way over here in the totally unfavorable towards modern hardware. So sometimes we can change the methods and data structures and shift over. But the problems we want to solve are often, you just don't have that much computation. So, but don't be afraid of more flops. Be much more afraid of memory motion. I guess the take-home message here. And what you actually attain, even with doing lots of optimizations, and this is coming out of the Berkeley optimization group, but they did a bunch of games they could play with, trying to tune the matrix operations for very specific hardware. And what you're getting out here is like 3% of peak or 5% of peak. And that's because you run into the memory bandwidth issues.
Well, Cloverton is an exceptionally bad machine that,
Yeah.
less than 10% of peak is
Yeah. Yeah, so often you can just compute the hard upper limit, which is a bandwidth bound. Yeah. So the typical kernel, if you have some compressed row storage, you have some loop over the rows and a loop over the columns, and you extract from the vector the value for that column, and you multiply it by the matrix entry. You never use the matrix entry or the column index again. So you had to load those, you throw them away. So just to, further point out the memory bandwidth limitations, and as you scale up on more cores, this is a really common thing. People are like, I ran this, on my workstation, and when I run it in parallel, it's not much faster, or occasionally even it's slower. Well, this tells that story. Sorry, the color here is not so good, but this is for Cray XT5. So here we have the total bandwidth for a node, for a socket, and then as we increase cores up to the 6 cores. And the per core bandwidth goes down quite a lot, and the aggregate bandwidth even peaks at 4, and adding the last 2 cores makes it worse. So BlueGene, in this sense, is a much better balanced machine in that you get pretty constant per core as you fill up the node.
You can imagine we have similar numbers for the Hopper with the 24
Yes.
cores, so it's a messier story.
Yes. Yeah, it's a messier story, but it's a similar story in the sense that using all of the cores doesn't help in terms of bandwidth. So sometimes it still improves performance a bit, but it's mostly not improving the sparse matrix multiply. So this is just the performance models for these blocked formats. So we'll use inodes, which is just identifying identical rows. And this allows us to skip some of the indices. So we're kind of, normally we needed to pull in a scalar and an integer for each non-zero in the matrix. And here we can pull in less than one integer per non-zero. And here we can pull in one integer per B by B block. This is with the explicit blocking. So you get a fair bit better performance here. And you can also get faster insertion because the block insertion does less searching. But I'm more excited about getting out of this box entirely and not using sparse matrices for the Krylov operator. So if you go unassembled, so this is a high-order finite element method, but where you store Jacobian information at quadrature points, then we're looking at the bytes of memory traffic per scalar entry in the result, or in the output vector of this matrix multiply. And so here we look at the memory as you increase the polynomial order and as you increase the block size. To say a block size of 3 would be elasticity, or 5 might be Euler equations. And this is the story if you go unassembled. And the same in terms of flops. So as soon as you go to second or at least to third order, the difference between these is so big, and actually the crossover in flops is pretty close, that the unassembled methods can win quite a lot. So arithmetic intensity, this is flops per byte, is at best 1/4 for an assembled method. Even for a dense linear algebra, it's 1/4, and you get about 10. So if the high order was buying you anything, then I think this is a useful approach. So increasing the order, otherwise doing things that can operate fast on, maybe using other classes of methods even, is a good way to improve performance. Question is, do you get better science? Sometimes you can get better science by using these kind of methods. Preconditioning, if you go unassembled, requires more effort. So having assembled matrices around so you can algorithmically test different preconditioning approaches is still really useful, even if your target is to not use assembled matrices.
On the unassembled, you will have to provide the preconditioning yourself.
Yes. So sometimes you can assemble a different matrix, which is cheaper to assemble, but is still effective for preconditioning. So I recommend having assembled matrices around whenever it's kind of reasonable from the code development perspective, because they let you try out lots of algorithms, and sometimes that's what you wanted to use. But when you're looking for kind of high throughput or ways to get around this memory bottleneck, going to higher order methods with unassembled Jacobians is, I think, a real useful approach. Yeah.
I'm a little confused if I have a problem where I have to have communication.
Yeah.
And I'm not using the assembled matrix method, and I have unassembled matrices, I still have to do communication.
Yeah, so this isn't about getting rid of the communication. That's kind of fundamental, that the operator needs these values that are held by a different process. So if we look at this, for example, we're not trying to cover the cost of communication. We're trying to use less memory locally. So the sparse format in the case of high-order finite element methods is horrible in terms of the number of bytes you need to store that linear operator. And storing values at quadrature points and using the kind of finite element machinery to apply the action is a much more compressed representation. But you had to write code for it. So it's not, the library can't magically, figure out what to do. So for performance, we want to be able to look at the cost of different stages or of different events. And so you can add these of your own for, say, pieces of the computation that you're doing, and call PETSI log flops. But all of the internal stuff in PETSI does these, and so you'll see these summaries. So there's a summary up front of how much time and messages and things like that have occurred, and then there's a per stage. I have it here. Let's see. So this will be really, really fast, and my screen isn't wide enough. So I've been running the debug thing, but we have this summary up top. I have this warning that I shouldn't profile with debugging. And then I have a bunch of events. So I have the nonlinear solve and function evaluation, and this has a bunch of details about messages and number of floating point operations and such. And we can look at that in more detail later when we're running jobs in the afternoon. Always send log summary if you have a performance question you want to ask on the mailing list or so. I will skip this. These examples we'll look at maybe some of them in the afternoon, and then I think I'm almost out of time, so I will give a real quick summary of new things in PETSI Dev. Yeah. So for multiphysics problems, we want a maintainable way to kind of package up code. And multiphysics problems, there's some examples here. So often these have stiff waves, such as plasma physics or combustion. Often there's saddle point problems. There's sometimes multi-domain problems or just problems of very mixed type. You combine radiation with some hydrodynamics. It's a very different process, or fluid structure as well. Almost any PDE-constrained optimization problem, so even if it's a single physics problem, has a lot of these same attributes. So we want, in terms of software, ways to package up the physics components in a maintainable way. Say if separate groups are developing those. We don't know a priori all of the methods we might want to use. So we have a much nicer interface for this now, where we maybe don't have this huge divide that there classically is between the monolithic methods, where you treat all the physics, all kind of bundled together, and the split methods, which are based on, say, some relaxation scheme or whatever, but where you work with the individual blocks separately and kind of, never or only in the Krylov iteration with the coupled system. So the data structures for for which class of methods you want to use are different, and how they interact with multigrid, which you likely want to use at least for some pieces, is also a bit different. So we now have a pretty nice way to do this, where you can take some system and it kind of gets packaged up in some hierarchy as you build a bigger and bigger system, and where we can switch between semi-implicit and fully implicit methods, lots of algorithmic choices, and matrix free wherever you want it. And so it's based on this kind of view of decomposing the problem. So at the top level, at least if you're using a fully implicit method, you would have some coupled space, and my colors here are representing, say, different physics, and these horizontal lines, we're dividing those among the processes. This is a possible, real simple decomposition, but we have, say, 3 physics on 3 processors. And so this is the global view. If we used a fully implicit time integrator, or we're solving a steady state problem, or a lot of, say, stability analysis problems, we want to work with this full space. So that's the top level view. In terms of communication, we can bring this down to local problems of that type. Or we could kind of go the other way and split into each physics component being separate. And then at the most local level, we have the single physics local problems. So these darker colors here are indicating the ghost values that we need, say, when evaluating residuals. So in my opinion, the nicest way to write maintainable software, and that kind of doesn't know too much, is to be able to write things that work with this local form. So like the residual evaluation, that sort of stuff. You want to be able to work with this local space where any neighboring values that you need have already been brought into your local vector. In terms of solving the equations, we're usually working with this or this form. So what we now have is an interface where you can get what I call a local submatrix. And so that's, you provide indices into this space for the submatrix that you wanted to pull out. And then you do the assembly here. And there's the same thing for vectors, but it's easier the software is easier for vectors. So you can assemble in this language, which I think is the most natural language to do assembly in. And then we'll put it back into a matrix that logically applies to this, but where the storage, and there's no copy in this process, but it's in the way that it's implemented. You can get a monolithic matrix that sits over here, or you can get a matrix that semantically sits here, but what it holds is nested blocks, and the nested blocks are applying to these vectors and the coupling between these vectors. So I think this interface is really slick. So you have a matrix, you have an index set for the rows and columns that you want to pull out, And these rows and columns are with respect to this space. And this is not a collective operation. You can call it locally. So the thing you get back, this matrix that gets returned to you, isn't guaranteed to implement matmult. So it's not necessarily a fully functional matrix, but you can insert values into it. So you can go call the set values, maybe the blocked variant. You can call the stencil variants as well. If you were using a nested format, then it just returns the nested submatrix. There's no copy, and it's fully functional. If you were using a monolithic format, it's going to return this sort of proxy matrix, and it's not a fully functional thing. It's just on the self communicator. So it has no parallel semantics. You can't use it for most matrix operations, but you can use it for assembly. So you call exactly the same API here for setting values. Those get translated into the indices of the parent matrix. So they get translated, these local indices get translated into these and inserted into the global matrix here. And actually, those levels of translation all get flattened. So there's one index translation when you call mat set values here, and it would go into this matrix. So the result is your code doesn't need to know at all. None of the assembly code needs to know even that it's building a matrix that's part of a bigger system. So you can package up the single physics, compile it and throw away the source code, and then link to that function that assembles the Jacobian for a block in the system, and we'll build exactly that block as part of a larger system. We have IMEX methods now, and a much nicer interface if you have DAE problems. So if you can write a possibly stiff system as some stiff part plus a non-stiff part, and then optionally you can provide a Jacobian with this predefined shift, then we can do these pretty neat IMEX methods. So you can use any implicit method for this. But you can also do, we have implemented these additive Runge-Kutta methods. So if you do ODEs, they're L-stable, which means they're good for very stiff problems. And you have a choice of the explicit method. So if you have strong stability properties, you can have that. They're order 2 through 5, embedded error estimates, and hot starts for Newton, and things like this. Special cases if G is linear. So this system that you get out, which is the Jacobian of the stiff part, is often still kind of challenging to solve because it might have a stiff wave in it or something that's difficult to precondition. But if you're working with some legacy code, so there's maybe you had some classical semi-implicit method, that turns out to make a good preconditioner for this system because this system will be very similar. But these methods are they're a bit more rigorous in terms of error control and not dealing with splitting or not committing splitting errors. So if you can separate the system into stiff and non-stiff, then these can be really robust. And we now have a single step interface. So if you want to control the time loop, but use PETSI time integrators, you can do that. So you can call a single step and then do whatever you want between steps. And variational inequalities. And this is the last of these points. So if you have problems with inequality or box constraints, we have semi-smooth Newton and active set methods you can use on that. And PETSI 3.2 will be released within a week or two. So we're using these for this interacts with, you can use multigrid and field split, and we combine those for some like phase field problems with long time steps to ensure this 0-1 criteria and for contact. So I don't know, ask me questions. Or we move on to the next speaker.
Yeah, so we're going to take a break now. So, and this afternoon, I'm sure that there are going to be a lot of questions when we're doing the hands-on. So, thank you.
Cool.